next speaker is David Keith.
Thank you very much. I'm going to give an argument about why we might want to learn more about this. And I'll say a little bit more about some recent research I've done that may give you a sense of what's possible, and also how much easier it is to come up with new ideas that might be interesting compared to the difficulty of actually figuring out their environmental risks or effectiveness. And in that sense, I think what I'm saying is quite in line with what you just heard. So there's no question that large-scale climate engineering is untested and dangerous. I think I would disagree quite strongly that it is doesn't exist. I think that the capacity to do it in engineering terms most certainly exists, and that's part of the reason we have to think seriously about how we manage that and how we build tools for figuring out how we regulate and manage that capacity, which I think is, in the sense that we have the capacity to build tall buildings or something, it's more or less a fact that if we wanted to, we could do this. And that itself has profound policy consequences, and I'm going to illustrate a little bit why I think that that's a reasonable statement. Let me first give you something that you could call a pitch, which is why it makes sense to think about understanding the effectiveness of this and perhaps building the capacity to do it contingent on what happens to the climate. So as presumably you all know, the amount of climate change we get for a given amount of CO2 emissions is still deeply uncertain by factors of 2 or 3. And the effects of climate change on, say, the cryosphere, the big ice sheets, are even more uncertain. So the climate problem has uncertainty at its heart. We don't know what the consequences of putting all that CO2 in the atmosphere will be. And this is crucial, CO2 lasts for a very long time when we put it in the atmosphere. The CO2 we put in the atmosphere, unless we have a technology for pulling it out later, the CO2 we put in the atmosphere has a footprint that lasts for thousands of years. A footprint, you might argue by some measures, that lasts much longer than the footprint of nuclear waste. And it's the combination of those two things, the uncertainty about the problem and the length of time of the footprint, that makes this problem so hard to manage. If you had only one of those things, it's much easier. Let's think a little bit more about inertia in the policy side as well. So we ought to have started, arguably, in 1965, when the first high-level report got to President Johnson explaining the dangers of putting all the CO2 in the air. We ought to have started to think about reducing our emissions, but clearly we didn't. When we actually have serious climate policy, which should have been decades ago but isn't yet, that policy is effectively going to build low-emission infrastructure, replace the high-emission infrastructure we have now. But that's a very slow process, because you've got to build all the capital stock of infrastructure, all the solar panels or windmills or nuclear power plants or whatever is your preference. And that capital stock builds slowly, and the emissions reductions are proportional to the amount of that low emissions stock you have. But emissions reductions don't directly affect the climate. It's the concentration, the buildup of CO2 in the atmosphere that affects the climate, and that's a second integral. And this makes this thing have enormous inertia. So from the time that we decide seriously to begin to pull emissions down, to the time that we see a big effect on the climate, has a timescale of order a century, or a good fraction of a century. And so it's that combination of uncertainty about how bad the climate response is and inertia that is, at least for me, one of the principal reasons that we might want to know something about these technologies. That's something both about how they work technically and beginning to think about how we'd actually manage them in terms of governance. Just to be even one more step precise, the point is, at some point, which could already be today, or could be 10, 20, 30, 40 years in the future, we may have put enough CO2 in the atmosphere that we'll have unacceptably huge responses to that CO2. And at that point, stopping emissions doesn't solve the problem. So it's common to frame this simply as a trade-off between doing geoengineering and cutting emissions. And there's no question that if you think about this as an optimization problem, there's some trade-off. But it is not simply a trade-off, because cutting emissions can reduce the amount of CO2 we're going to put in the atmosphere in the future, but it does nothing to manage the amount of CO2 we have already put in the atmosphere. And the various kinds of geoengineering could potentially do that. So let's start out by distinguishing two totally different sorts of things that have both come under the name geoengineering, but I think have very little to do with each other with respect to the underlying science technology, with respect to the costs, and with respect to the social science and governance issues they raise. So one of those things is the thing that I'll mostly talk about, and I'll give you some specific new research on, is how we might manage or control or affect, is maybe a more honest word, the amount of sunlight that the Earth absorbs. And I'll come back to that in a minute, but the key factors are this is fast, it's cheap, and it's inherently imperfect. It cannot compensate for the amount of CO2 in the air. There are a bunch of other things we might do to remove CO2 from the air. There's a big list, and full disclosure, one of those on the list, the direct capture of CO2 from the air, I work on a commercial basis. I do absolutely no proprietary commercial work on soil radiation management because I think such work would be wrong. But on carbon cycle engineering, there's a whole range of things we can do, but all of those things are inherently slow and expensive. But on the upside, they actually get the CO2 out of the air, which is the root problem, and in some sense would allow you to go backwards. So partly because it's fun new work, and that's the point of conferences, and also because it raises a bunch of the key governance issues in interesting ways, I'll tell you a little bit about some new work we've been doing, thinking about how you actually might put aerosols in the stratosphere. And that lists some of my collaborators. So almost all the work, not all, but almost all the work and almost all the modeling that's looked at putting sulfate aerosols in the stratosphere has assumed that we'd mimic volcanoes. And there's a lot of sense to thinking that we mimic volcanoes because we have some sense of what's happened after volcanoes. The planet cooled, there were impacts on ozone, there were impacts on the biosphere, we were able to monitor them. But there's some reason to think that for continuous injection, this won't work very well. And the reason basically is the way those things work is you put a gas which does not condense, SO2, into the stratosphere. And the only way it makes particles is it converts to H2SO4, sulfuric acid, and then that stuff, which isn't volatile, condenses onto particles. And that automatically happens slowly if you're putting a gas in like SO2. And because it happens slowly, you necessarily find that almost all of the new mass you put in ends up on existing particles, either directly or by making ultrafine particles that then coagulate with the big particles. And so the problem is you end up making particles that are too small, too large, if you do this continuously. This gives you a sense of how important particle size is. So on the x-axis, sorry, you can't read as well as radius and microns. And look at the alumina or sulfuric acid functions, which are the mass-specific backscatter. So a measure of radiative forcing. In fact, I have it in watts per square meter per megaton. And those things fall off as the particles get larger. But even more important, the fall speed rises quite rapidly in this regime. And so as particles stick together and get large, they fall out of the stratosphere very quickly. And so particles that are too large are much less effective per unit mass. So